A half-wave rectifier is the simplest way to turn an AC sine wave into a pulsating DC. Imagine a water valve that only opens when the water pressure, the AC voltage, is pushing in the forward direction and stays closed when the pressure reverses. The circuit consists of a single diode in series with the load. During the positive half cycle, 0 degrees to 180 degrees, the diode is forward biased, so current flows and the load sees the same voltage shape as the source, except for the small diode drop, approximately 0.7 volts for silicon. During the negative half cycle, 180 degrees to 360 degrees, the diode is reverse biased. It blocks current and the load voltage drops to 0. The output waveform therefore looks like a series of positive half-sine pulses separated by flat zeros. The peak value of the output voltage is essentially the peak of the AC source minus the diode drop. Vout peak is approximately Vs peak minus Vd. If the source is 12 volts RMS, its peak is Vs peak equals 12 times square root of 2, approximately 17 volts, so the rectified peak is approximately 16.3 volts. The key points: only one diode conducts. Output exists only during one half of the AC period. The average DC level is low because the waveform spends half the time at 0. A center-tapped full-wave rectifier uses a transformer with a secondary winding that has a tap at its electrical center. Think of the tap as the middle of a seesaw. When one side goes up, the other goes down. Two diodes are connected to the outer ends of the secondary, and the center tap is tied to the ground or the negative side of the load. During the first half cycle, the left half of the secondary becomes positive with respect to the center tap, forward biasing diode D1. The right half is negative, keeping diode D2 off. During the next half cycle, the roles reverse. D2 conducts while D1 is off. Thus, every half cycle produces a positive voltage across the load. The output waveform consists of consecutive positive half-sine pulses, but now there is no gap of 0 voltage. Vout peak approximately Vs peak minus Vd, where Vs peak is the peak voltage of one half of the secondary winding. If the transformer secondary is 12 volts RMS on each half winding peak is 12 root 2 approximately 17 volts, so the rectified peak after diode drop is approximately 16.3 volts. Because both halves of the AC cycle are used, the ripple frequency, the rate at which the output repeats, is twice the line frequency. For example, 120 Hz in a 60 Hz system. The full-wave bridge rectifier removes the need for a center-tapped transformer by using 4 diodes arranged in a diamond shape. Imagine a 4-way traffic roundabout where traffic can only flow clockwise. Regardless of which side the cars, current, enter from, they are forced around the same direction toward the load. During the positive half cycle of the AC source, diodes D1 and D2 become forward biased, while D3 and D4 are reverse biased. Current flows from the source through D1 across the load and returns via D2. In the negative half cycle, D3 and D4 conduct, creating the same polarity across the load. Hence, every half cycle delivers a positive voltage to the load. The output waveform is again a continuous series of positive half-sine pulses, identical in shape to the center-tapped case, but the peak voltage is now limited by the total secondary voltage of the transformer, no center tap. If a 12-volt RMS transformer is used, its peak is 12 times square root of 2, approximately 17 volts, and after 2 diode drops about 1.4 volts total, the peak is about 15.6 volts. Vout peak is approximately Vs peak minus 2 times Vd. The bridge type is popular because it works with a simple single-winding transformer and provides the same full-wave benefit: higher average voltage, lower ripple, and a ripple frequency of 2F line. Average DC output voltage. Half-wave, the average value over one full AC period T, is the integral of the positive half sign divided by T. VDC half equals 1 over T integral from 0 to T over 2 of Vm sine omega T dt equals Vm over pi, where Vm is the peak of the source, or Vm minus Vd if diode drop is considered. For a sinusoid of RMS value Vrms, Vm equals root 2 times Vrms, so VDC half equals root 2 over pi times V RMS, approximately 0.45 times V RMS. Full wave center tapped or bridge. Both half cycles contribute, so the period of integration is t over 2, the waveform repeats every half cycle. VDC full equals 2 over t integral from 0 to t over 2 of Vm sine omega t dt equals 2 Vm over pi. Thus, VDC full equals 2 root 2 over pi times V RMS, approximately 0.9 times V RMS. RMS output voltage. Half wave, the RMS value represents the heating effect of the pulsed output. V RMS half equals root of open brace 1 over t integral from 0 to t over 2 of Vm sine omega t squared dt close brace equals Vm over 2. V RMS full equals root of open brace 2 over t integral from 0 to t over 2 of Vm sine omega t squared dt close brace equals Vm over root 2. These formulas are useful for sizing components and calculating power. Numerical example. Assume a 12-volt RMS transformer, silicon diodes VD approximately 0.7 volts. Half wave, Vm equals 12 times root 2 equals 16.97 volts. VDC approximately open parenthesis 16.97 minus 0.7 close parenthesis over pi equals 5.17 volts. VRMS approximately open parenthesis 16.97 minus 0.7 close parenthesis over 2 equals 8.14 volts. Full wave bridge, Vm equals 16.97 volts. VDC approximately open parenthesis 16.97 minus 2 times 0.7 close parenthesis times 2 over pi equals 9.26 volts. VRMS approximately open parenthesis 16.97 minus 2 times 0.7 close parenthesis over root 2 equals 10.9 volts. Efficiency eta. Efficiency is the ratio of DC power delivered to the load, PDC, to the AC power drawn from the source, PAC. Eta equals PDC divided by PAC. For an ideal diode, no loss, the theoretical maximum efficiencies are half-wave eta max equals 40.6%. Full-wave bridge or center tapped eta max equals 81.2%. These come from substituting the average and RMS values derived earlier. Eta half equals VDC squared divided by RL over V RMS squared divided by RL equals VDC divided by V RMS squared equals 0.45 squared, approximately 0.206, which is 20.6% real diodes lower. The textbook figure 40.6% includes the diode drop. Power factor PFs. Power factor measures the phase relationship between voltage and current. For rectifier circuits, the current is non-sinusoidal, so we use the displacement power factor, cosine phi, multiplied by the distortion factor. PF equals real power divided by V RMS times I RMS. Because current flows only during part of the cycle, PF is lower than 1, typically 0.6 to 0.9 for full-wave rectifiers. Ripple factor R. Ripple factor quantifies the remaining AC component in the DC output. R equals the square root of V RMS squared minus VDC squared, divided by VDC. For a simple half-wave rectifier with no filter, R half approximately 1.21. For a full-wave rectifier, R full approximately 0.48. Adding a smoothing capacitor reduces R dramatically. The ripple voltage peak to peak for a capacitor filter is approximated by delta V approximately I load divided by F ripple times C, where F ripple equals F line for half wave and 2 times F line for full wave. Example calculation. A 12-volt RMS, 60 Hz source drives a full wave bridge feeding a 100 ohm load. VDC approximately 9.3 volts from previous example. IDC equals VDC divided by RL, approximately 0.093 amperes. PDC equals VDC times IDC, approximately 0.86 watts. VRMS approximately 10.9 volts. IRMS approximately 0.1 amperes. PAC equals VRMS times IRMS, approximately 1.09 watts. Eta approximately 0.86 divided by 1.09, approximately 0.79, which is 79%. Ripple no filter R approximately 0.48, delta V approximately R times V DC, approximately 4.5 volts peak to peak. If a 2200 microfarads capacitor is added, delta V approximately I load divided by 2 times F times C equals 0.093 divided by 120 times 0.0022, approximately 0.35 volts, giving R approximately 0.038, much smoother. Load resistance effect. When a load draws current, the voltage across it drops due to both the transformer winding resistance, RS, and the diode's dynamic resistance, RD. The output voltage under load is V out load equals V no load minus I load times, open parenthesis, RS plus RD close parenthesis. Voltage regulation measures how much the output changes from no load to full load. Regulation percent equals open bracket V no load minus V full load close bracket, divided by V full load close bracket times 100. A well-designed rectifier with low RS and large filter capacitor shows less than 5% regulation. Source transformer resistance. The transformer's secondary resistance adds to the voltage drop and also limits the maximum current. RS prime equals open parenthesis NP divided by NS close parenthesis squared times RP. For a given turns ratio NP over NS, the reflected primary resistance appears as. So choosing a transformer with adequate wire size, low RS, is essential for high current rectifiers, for example power supplies. Explanation: selecting the transformer. 1. Determine the required DC voltage, V sub DC, after rectification and diode drops. 2. Choose the secondary RMS voltage, V sub sec, RMS such that half-wave DC voltage is approximately open parenthesis V sub sec, peak minus V sub D close parenthesis divided by pi, leads to V sub sec, RMS is approximately open parenthesis pi times V DC close parenthesis divided by square root of 2 plus V sub D divided by square root of 2. Full wave bridge DC voltage is approximately 2 times open parenthesis V sub sec, peak minus 2 V sub D close parenthesis divided by pi, leads to V sub sec, RMS is approximately open parenthesis pi times V DC close parenthesis divided by 2 times square root of 2 plus V sub D times square root of 2. 3. Calculate the turns ratio using the primary line voltage, V sub line, RMS, and the chosen secondary RMS voltage. N sub P divided by N sub S equals V sub line, RMS divided by V sub sec, RMS. Example: half wave. Desired DC output 12 volts. Assume silicon diode 0.7 volts. Solve for V sub sec, peak. 12 equals open parenthesis V sub sec, peak minus 0.7 close parenthesis divided by pi, leads to V sub sec, peak approximately 12 pi plus 0.7, approximately 38.1 volts. Thus V sub sec, RMS equals V sub sec, peak divided by square root of 2, approximately 26.9 volts. If mains is 230 volts RMS, turns ratio 230 divided by 26.9, approximately 8.55. A standard 24 volts RMS secondary, approximately 34 volts peak, would give a slightly higher DC, approximately 10.6 volts after diode, acceptable with regulation. Example: full wave bridge. Desired DC 12 volts. 12 equals 2 times open parenthesis V sub sec, peak minus 2 times 0.7 close parenthesis divided by pi, leads to V sub sec, peak approximately open parenthesis 12 pi divided by 2 close parenthesis plus 1.4, approximately 20.4 volts. V sub sec, RMS approximately 20.4 divided by square root of 2, approximately 14.4 volts. For 230 volts primary, 230 divided by 14.4, approximately 16.0. A 15 volts RMS transformer, approximately 21.2 volts peak, is a common choice, giving a DC of about 12 volts after diode loss. The key points. Use a margin of 10 to 20% to cover regulation loss. For high current supplies, keep the secondary current rating greater than or equal to I load, plus a safety factor. Choose wire gauge to keep R sub S low, improving regulation and efficiency. Half-wave rectifier voltage. A 120-volt RMS 60 Hz transformer secondary feeds a half-wave rectifier with a silicon diode V sub D equals 0.7 volts. Load resistance is 500 ohms. Find the peak output voltage, the average DC voltage, and the ripple voltage peak to peak assuming no filter capacitor. Solution outline. V sub sec peak equals 120 times square root of 2 approximately 170 volts, leads to V out peak equals 170 minus 0.7, approximately 169.3 volts. VDC equals V out peak, divided by pi approximately 53.9 volts. IDC equals VDC, divided by 500 ohms approximately 0.108 amperes. V RMS of output approximately V out peak, divided by 2 approximately 84.6 volts, leads to I RMS approximately 0.169 amperes. Ripple factor R equals square root of V RMS squared minus VDC squared, divided by VDC approximately 1.21, leads to delta V equals R times VDC approximately 65 volts. Full-wave bridge regulation. A 24-volt RMS 50 Hz transformer supplies a full-wave bridge rectifier feeding a 100-ohm load. The secondary resistance is 1 ohm and diode forward resistance is 0.1 ohms each. Compute the no-load DC voltage, the load voltage, and the percentage regulation. Solution outline. V sub sec peak equals 24 times square root of 2, approximately 33.94 volts. No load VDC, approximately 2 times open bracket V sub sec peak minus 2 times 0.7 close bracket, divided by pi equals 2 times open bracket 33.94 minus 1.4 close bracket, divided by pi approximately 20.7 volts. Load current I equals VDC divided by open bracket RL plus 2 times RD plus RS close bracket equals 20.7 divided by open bracket 100 plus 0.2 plus 1 close bracket approximately 0.203 amperes. Load VDC equals I times RL approximately 20.3 volts. Regulation equals open bracket 20.7 minus 20.3 close bracket divided by 20.3 times 100 approximately 2.0%. Capacitor filter ripple. Design a filter capacitor for a full-wave bridge rectifier that limits the ripple voltage to less than or equal to 0.5 volts peak to peak. When supplying 0.5 amperes at 12 volts DC, the line frequency is 60 Hz. Solution outline. Ripple frequency, FR equals 2 times 60 equals 120 Hz. Required C equals I load divided by open bracket, FR times delta V close bracket equals 0.5 divided by open bracket, 120 times 0.5 close bracket, approximately 0.00833 farads equals 8,300 microfarads. Choose a standard 10,000 microfarad electrolytic for margin. These questions test understanding of waveforms, calculations, and design trade-offs typical for electronics engineering exams.